Hello and welcome back to Physical Geology. This is part 2 of the Lab 1 Intro to Science, and I'm going to start looking at a conversion problem with microliters and milliliters. But then after that I go into scientific notation, significant digits, and experimental error. And then that'll wrap it up. There's a lab, in fact I did this problem in your online lab, and it was a little difficult because we need to know that one milliliter is 1,000 microliters, right? So this funny symbol here is a Greek letter mu, mu, but it's for micro because we already use m for a milli, right? And so so there's 1,000 microliters in 1 milliliter. And the other way to think about it, there's in 1 liter there's 1,000 milliliters, right? So this is a very small amount. And the problem is that we only have this microliter pipette. So that's one of these microliters here. And they want you to make this 1% solution here. You can kind of work that one out, but I'm going to work out a similar problem here that'll help you, or maybe it can help you guide you for when you do this on your own here. So one of the first things we want to do whenever we see percent problems, think of percent as, we know 2 out of 100. That's percent. So this 2% just means 2 out of 100. And we want, in our final product, we want 500 microliters, or milliliters that is, of some solution, but we don't know how much we need to add. This is our unknown here, right? That's our variable. So but the problem is, remember we only have a microliter pipette, right? Only have a microliter pipette. So we need to really convert this, use a number here that's going to be in microliters, right? So I need to multiply this by 1,000, right? So that's really going to be 500,000 microliters, right? And so to do this problem, we'll just rewrite it down over here. 2% is what out of 500 microliters, right? Because I'm going to have to add those microliters to make that 2% solution. And so when I do this problem, basically, I'm going to multiply 500,000 times 2, which is basically 1,000,000 microliters, and I'm divided by 100, right? Because I still have this 100 here, and that's going to give me 500,000 microliters. So that's my answer. So you'll see when you do your problem on Angel, or it's not an Angel, but on eScience Labs, because there's a problem that you'll have to do this. You just make sure you use a bigger volume here, or sorry, a bigger number for this smaller volume or smaller concentration of microliters here, right? So there is an example there. Now the next part here deals with significant figures. There's I kind of wrote this out based on the material in the eScience lab, but some of you may not have access to it. But let's just look at some rules. Any non-zero number is significant, right? Any non-zero. So 0.45 has 2 significant figures. 3.99 has 3 significant figures. Anytime a 0 appears between significant numbers, the 0 is significant. So for example, these 2 are significant and these 3 are significant. This one is not, right? So this number has 4 significant figures. This one has 6 significant figures. Now, zeros that are ending numbers after a decimal point, or zeros after significant numbers before a decimal point, are significant, right? So for example, 45.00, well, that looks like a pretty precise number, so it has 4 significant figures. 15.0100.00, well, all these zeros are significant. So they're saying these are significant and so are these, right? So that one will have 8 significant figures. Zeros that are used in placeholders before other digits are not significant. So in this example, only those 2 are significant. Only those 2 are significant. Now, zeros at the end of a number with no decimal point can be significant. And so, for example, 50 would have 2 significant figures, but 3,000, well, it could have 1, 2, 3, or 4. And in fact, there's a quiz problem on the eScience lab quiz where it asks you, it asks how many significant figures in a number just like this, and you have to pick all the options because it could be all of them, 1, 2, 3, or 4, and hopefully you'll run into that one. And then finally, when you're adding, subtracting, dividing, multiplying numbers, your answer always will always have the same number of significant decimal places as the least precise number. For example, when you add 4.2 and 8.97, well, your answer is 13.17, but you only can go 2 significant figures, so your answer will be 13.2, so you have to round this up over here, right? When you're multiplying 28.8 times 54.76, you get a big number, right? That's you can't use it because your smallest number here is 3 significant figures. So here we'll take it into 1580. That's the closest we can get right there. Now, scientific notation, right? So it's really a way of expressing big numbers or small numbers in an easy format, right? And so there are several components. The exponent is the small number there. The base would be this number here, and the coefficient is this first number there. Now let's convert these numbers into scientific notation, right? So the key thing is this will have 5 significant figures. So we're going to have to move this over. So we go 1, 2, 3, 4, 5. We're going to move it over 6 times. So it's going to be 5.6. But I'm going to keep these significant figures here. 108 times 10 to the 6th power, because I went back here to the 6th power. So that would be the answer to that one. For this one, we only have 2 significant figures, but we're going to have to move forward 1, 2, 3, 4, 5, 6. So this is also going to be 2.5 times 10 to the minus 6. 10 to the minus 6 there, right? Because it's a small number, right? This is a small number, so we move the decimal point in that direction to give us back to this number here. And then for 5300, since we only have 2 significant figures here, we're going to go 5.3 times 10 to the 3, right? Because we're moving 1, 2, 3. And then this one, we're going to make it 1.2 times 10 to the 1, 2, 3, 4, 5, right? And that's going to be negative 5, right? Because again, it's a small number there. So kind of review these, look at some, do your own research there, and there are some quiz questions on some significant figures there and scientific notation. Now the last part here deals with this percent error, and the percent error, and we'll be doing some measurements. You'll be doing some measurements on your own in lab. Your lab kit comes with a scale and a volume and a graduated cylinder, so you'll be measuring volumes and masses, right? So there's an experimental value. That's what you measure, what your data gives you, what you observe, and the actual value is the accepted value, right? So it's always the experimental minus the actual. And then these terms here, these 2 bars mean absolute value, which means regardless of what the answer becomes up here, if it's negative or positive, you always have to make it positive, right? So if I get a negative 2 up here, it's going to be just 2. It's the absolute value term. And then we're going to multiply that by 100, right? So let's look at an example I have over here. So say you're determining the boiling point of ethanol. Your experimental observation was 172.3 degrees Fahrenheit. But the actual boiling point is 78.3, but they give it to you in degrees centigrade. So the first thing you have to convert. And so remember, degrees centigrade is degrees Fahrenheit minus 32 divided by 1.8. Right, so to do that, we're going to put our 172.3 degrees Fahrenheit minus 32, and we're going to divide that by 1.8, and that should give us degrees centigrade, right? So if we go back to our calculator here, we go the 172.3 minus 32, and they divide that by 1.8. that gives us 77.9 degrees centigrade. So this is our actual, or sorry, our experimental, right? So that's we took this number, right? Our experimental. So now we have the actual already. So for percent error, we're going to take that experimental, which is 77.9 degrees, minus the 78.3 degrees, absolute value of that, divided by the 78.3 degrees, and then times 100. So when we do this, we'll take the 77.9 minus 78.3. That gives me a negative 0.4, but in reality it's going to be a positive 0.4. So it's going to be 0.4 divided by 78.3. So we'll make this a positive, and we'll take divided by 78.3, and that's 0.0051 times 100. So basically that becomes 0.5% error, which is within the accepted value there, right? So let's go back here, right? So anyways, that's how we're going to calculate percent error. I hope this helps. Go through your lab. Again, answer those lab sheets, scan them, and turn them in.